calculus. The word itself might sound intimidating, conjuring up images of complex equations and abstract theories. For many, it brings back memories of high school math classes filled with daunting problems and sleepless nights. But fear not. At its heart, calculus is a powerful tool that unlocks the secrets of change. It's not just about solving equations, it's about understanding the very fabric of our world. It provides a language to describe motion, growth, and transformation in the world around us. Whether it's the way a river carves its path through the landscape, or how a plant grows towards the sunlight, calculus helps us make sense of these dynamic processes. From the smallest atom to the largest galaxy, calculus helps us understand how things change over time and how different quantities are related to each other. It bridges the gap between the micro and the macro, offering insights into the fundamental workings of the universe. Imagine trying to predict the trajectory of a rocket launching into space, or understanding the spread of a virus through a population. These are not just theoretical exercises. They have real-world implications that affect our daily lives. These complex phenomena involve constantly changing variables. Traffic patterns, weather systems, and even the stock market. All of these can be analyzed and understood through the lens of calculus. Calculus provides the mathematical framework to model and analyze these changes, giving us the power to make predictions and solve real-world problems. Engineers, scientists, and economists all rely on calculus to innovate and make informed decisions. Throughout history, brilliant minds have been captivated by the challenge of understanding change. Isaac Newton and Gottfried Wilhelm Leibniz, the pioneers of calculus, laid the groundwork for centuries of scientific advancement. From the ancient Greeks grappling with the concepts of infinity and motion, to the modern-day scientists using calculus to unravel the mysteries of the universe, the journey has been long and filled with remarkable discoveries. Our understanding of calculus has evolved over centuries. Each generation of mathematicians has built upon the work of their predecessors, refining and expanding the scope of this incredible field. This essay will take you on a journey through the fascinating world of calculus. We will delve into its origins, explore its fundamental principles, and see how it has shaped our understanding of the natural world. We'll explore its rich history, key concepts, and its profound impact on science, technology, and our understanding of the universe. From the development of computer algorithms to the modeling of climate change, calculus is at the heart of many modern advancements. So, buckle up and get ready for an exciting adventure into the world of calculus. Whether you're a student, a professional, or just a curious mind, there's something here for everyone. Let's unlock the secrets of change together.
The roots of calculus can be traced back to ancient civilizations that grappled with the concepts of area, volume, and rates of change. The ancient Greeks, in particular, made significant contributions. Eudoxus of Cnidus developed the method of exhaustion, a precursor to integral calculus, to calculate the area of curved shapes. Archimedes, a renowned mathematician and inventor, further refined this method and used it to calculate the volume of spheres and other complex shapes. These early mathematicians provided the foundation upon which calculus would later be built. However, it wasn't until the 17th century that calculus as we know it today began to take shape. The scientific revolution was in full swing, and there was a growing need for new mathematical tools to describe the laws of motion, gravity, and other physical phenomena. This need paved the way for the independent discoveries of calculus by Isaac Newton and Gottfried Wilhelm Leibniz. Isaac Newton and Gottfried Wilhelm Leibniz, two towering figures in the history of mathematics, are credited with independently developing calculus. Their contributions have left an indelible mark on the scientific world, shaping the way we understand and interact with the universe. Their groundbreaking work revolutionized mathematics and science, providing a powerful tool for understanding the universe. Calculus, with its ability to describe change and motion, became a cornerstone of modern scientific inquiry. Newton, an English physicist and mathematician, developed his version of calculus, which he called fluxions, in the mid-1660s. His approach was deeply rooted in his studies of motion and the forces that govern it. He used it to solve problems related to motion, optics, and gravity. Newton's laws of motion and his law of universal gravitation were all formulated using his calculus, providing a new framework for understanding the physical world. His masterpiece, the Principia Mathematica, laid the foundation for classical mechanics and revolutionized our understanding of the universe. This work not only showcased his mathematical prowess, but also demonstrated the practical applications of calculus in explaining natural phenomena. Leibniz, a German mathematician and philosopher, developed his version of calculus independently around the same time as Newton. His approach was more focused on the abstract and theoretical aspects of mathematics. He introduced the notation and symbols we still use today, such as the integral sign and the derivative notation. These notations have become fundamental in the field of mathematics, making complex calculations more accessible and understandable. Leibniz saw calculus as a powerful tool for understanding change and continuity, and his work had a profound impact on the development of mathematics in Europe. His contributions extended beyond calculus, influencing various fields such as logic, philosophy, and engineering. The independent discoveries of calculus by Newton and Leibniz sparked a bitter priority dispute that lasted for centuries. This controversy, known as the calculus priority dispute, involved accusations of plagiarism and intense nationalistic pride. While both mathematicians made significant contributions, it is now generally accepted that they arrived at their discoveries independently. The dispute, however, highlighted the competitive nature of scientific discovery and the importance of proper attribution in the academic world. Their work laid the foundation for modern calculus and continues to shape our understanding of the world today. The principles they established are taught in classrooms around the globe and are applied in various scientific and engineering disciplines, from predicting planetary motion to designing complex machinery. The legacy of Newton and Leibniz lives on, as their discoveries continue to inspire new generations of mathematicians and scientists. Their independent yet parallel journeys in developing calculus remind us of the boundless potential of human ingenuity and the profound impact of mathematical thought on our understanding of the universe.
Section 4. Limits. Approaching the infinitely small. One of the fundamental concepts in calculus is the concept of a limit. Imagine approaching a wall. As you get closer and closer, the distance between you and the wall decreases. The limit of this distance as you get infinitely close to the wall is 0. This idea of getting infinitely close to something without actually reaching it is at the heart of limits. In calculus, limits allow us to describe the behavior of functions as they approach certain values. This is crucial for understanding how functions behave near points of interest. They provide a way to deal with infinitely small or infinitely large quantities, which are essential for understanding concepts like continuity, derivatives, and integrals. Without limits, these fundamental ideas in calculus would be impossible to define rigorously. For example, consider the function f of x equals 1 over x. This function behaves interestingly as x approaches 0. As x gets closer and closer to 0, the value of the function becomes increasingly large. This illustrates how limits can describe the behavior of functions that grow without bound. We say that the limit of f of x as x approaches 0 is infinity. This means that as x gets arbitrarily close to 0, f of x increases without any upper limit. Limits provide a rigorous framework for dealing with such situations, allowing us to make sense of the behavior of functions at points where they might not be defined. This is particularly useful in real-world applications, such as physics and engineering, where understanding the behavior of functions at specific points can be critical. For instance, consider a car approaching a stop sign. As the car gets closer to the stop sign, its speed decreases. The limit of the car's speed as it reaches the stop sign is 0, just like the distance example we discussed earlier. Limits also help us understand time intervals that get smaller and smaller. In physics, this is crucial for understanding motion and change over time. By using limits, we can make sense of continuous functions, ensuring that there are no abrupt changes or gaps. This smoothness is essential for many mathematical models and real-world phenomena. The concept of limits is not just confined to mathematics. It permeates various scientific fields, providing a foundational tool for researchers and engineers to model and understand complex systems. As you delve deeper into calculus, you'll find that limits are the building blocks for many advanced topics. Mastering this concept will open doors to a deeper understanding of the mathematical world. So, as you continue your journey in learning calculus, remember that approaching the infinitely small through limits is a powerful tool that will enhance your mathematical intuition and problem-solving skills. Section 5. Derivatives, the language of motion and change. The derivative is one of the most important concepts in calculus. It measures the instantaneous rate of change of a function. In other words, it tells us how much a function is changing at a particular point in time. Imagine driving a car. Your speedometer tells you your instantaneous speed, which is the rate at which your distance is changing with respect to time. The derivative gives us a way to calculate this rate of change for any function, not just distance and time. Derivatives have countless applications in physics, engineering, economics, and other fields. For example, in physics, velocity is the derivative of position, and acceleration is the derivative of velocity. In economics, marginal cost is the derivative of the total cost function. Derivatives provide a powerful tool for analyzing and predicting change in a wide range of phenomena.